All right, so I'm going to take a look at two things in this video. We're going to look at the divergence test, and then we're going to take a look at the integral test. All right, now first, let's take a look at the divergence test. And now, really straightforward. I think here's one of the easiest, when we're talking about series, the easiest and most straightforward test to do. And it's always worthwhile just even mentally to start off, if you're given a series and you're asked, does this series converge, to just check the divergence test. All right, now here is what the divergence test tells me. It says if the limit of a sub n as n goes to infinity is equal to c, right? And c, it just says some value. The important part is that it's not 0, right? Or the limit of a sub n does not exist, then the series diverges, right? Really straightforward, right? It goes back to looking at the terms of the sequence, right? If the terms of the sequence do not converge, right? Do not converge to 0, I should say, then the series itself is also not going to converge. It will diverge. So, for example here, let's take a look at the limit as n goes to 1 of infinity, n squared over 5n squared plus 4. Right? If I just take a look at the limit as n goes to infinity of n squared over 5n squared plus 4, right? We see again, right, these are of the same power, so the coefficients take over. So as n goes to infinity, we have 1/5. So what the divergence tells me is that this, again, diverges. All right. Okay, and then the same thing here, right? Let's take a look at another example. N goes to 1 to infinity of v 1 over n squared. All right, so it says again, just focus on the limit of the terms of the sequence, not the series itself. All right, so as this goes to infinity, this fraction here is going to 0, but e to the 0, that's going to 1. Right, so again, a finite value. So what that tells me is that this diverges. Okay, now it's important here that again, a common mistake here is really misinterpreting what this theorem is telling me. Notice that this is not a convergence test, right? This only tells me if a series diverges if this particular limit has a non-zero value, right? Or it does not exist, right? Like think of maybe it's an alternating type sequence where it goes from positive to negative, right? Or between other two values. Okay, so just keep that in mind, what can be inferred or concluded from this theorem, this test. And for example, let's take a look at a harmonic series, which we covered in a previous video. Is equal to 1, to infinity. Okay, now if we look here, we see here that this goes to 0. All right. Now, it's important here to realize that the divergence test does not apply here. Okay, the divergence test is actually inconclusive, right? If we go back and look at what the divergence test tells me, again, watch those if-then statements, right? If it's true, right? If it is some non-zero number, if we actually have a 0 number, the divergence test does not apply. All right, so it's important to realize that here, that this, in this case, the divergence test does not apply. All right, and in fact, even if we take a look at another one here, 1 over n squared, right? And we have the same behavior. The limit as n goes to infinity of 1 over n squared, right, equals to 0. Now, in both of these cases, the divergence test does not apply, right? Whenever those sequence terms are going to 0, the divergence test does not apply. It is inconclusive, right? It's not telling me that it actually converges, right? Because we'll see, what we've seen the harmonic series already, we've shown that this diverges. And this shortly will show this actually converges. Okay, so just keep that in mind, all right? It's important here that we interpret the divergence test correctly, all right? It only applies when the limit of the sequence terms are non-zero, right? The limit is non-zero as n goes to infinity, right? Or the limit does not exist, okay? All right, so that brings us then to our integral test. Integral test. All right, so let's say, for example, I want to connect kind of our continuous functions with our kind of discrete series here and have like a way to connect both of these, right? So I'm going to take a look at my function f of x equals to 1 over x. Okay, and I'm going to set up here these rectangles, right, of length 1. Right, so essentially the area is going to be the height of the rectangle, which can be done by the function value, right? If we go 1, 2, 3, 4, 5, 6. Okay, so here when x is 2, right, this is 1/2, 1/3, 1/4, and 1/5, right? So area is 1. Again, x value of the height, this is 2. That's 1 here. 2, right? So that's 1/2, 1/3, 1/4, 1/5. All right. Okay, and notice here if we take the interpretation of the integral as area under the curve here, then we can see that the rectangles constructed in this way, right, lie above the function itself. So we can say that in this particular case, right, if I keep going here, all right, this is for 6, we could say if I look at the kth partial sum, 1 to k of 1 over n, right, so we get 1 plus 1/2 plus 1/3. If I continue with the same excuse me, with this same kind of right, notation or same kind of pattern, I could see that the sum is going to be greater than the integral of 1 up to k plus 1, right? And why k plus 1? And we could see from our drawing here, when we go, the fact that we start on the right here at 1, right? When we go to 6, we get that last rectangle is 1/5. So we kind of go one further of 1 over x dx, right? So here it just is a matter of comparing areas, right? And we could say this partial sum f sub k is greater than the integral of 1 over k plus 1, 1 over x dx, right? Which again here, the straightforward integral is the natural log of x evaluated at k plus 1, which is just equal to ln of k plus 1, since ln of 1 is 0. So now what we've established is that the kth partial sum is bigger than the natural log of k plus 1. So now what we do is, well, we can treat this almost like an improper integral, right? If k plus 1, I let that go to infinity, right? So if I take here the limit as k goes to infinity of ln of k plus 1, as n goes to infinity, again, ln increasing function, so as ln goes to infinity, right, as k goes to infinity, excuse me, ln also goes to infinity. Now, how does that help with the series? Well, what is the inequality that I have going here? All right. I have that my kth partial sum is larger than infinity. Well, it means that it is unbounded, right? That the sum itself is really big, right? It's bigger than infinity, right? Again, this brings up another idea of sizes of infinity, right? Which we've kind of talked about when we talked about like L'Hopital's growth rates and even back in limits, right? The idea of having a ratio of infinity over infinity, right? So there are this idea of bigger infinities, right? But again, compared here, right, when we have something like this, what that integral is telling me, since that integral is going to infinity, the kth partial sum is also going to infinity as well, right? Because it's larger than that integral. So what that tells me is that using the integral, right, I have shown that this sum of 1 over n is divergent because their partial sums, right, are larger, they're unbounded essentially, right? The kth partial sum as k goes to infinity, they're getting larger and larger and larger, right? They're unbounded. Okay, so I've done that now a second way, right? The first way I did using those partial sums where I looked at every power of 2. Now I did this using an integral, right? And I've arrived at the same conclusion, which should be the case. All right, now let's take a look at a different series here. How about we take a look again here? All right, 1, 2, 3, 4, 5, 6. Take a look here at, how about the function 1 over x squared. Excuse me. Okay, so here I have 1, 2, 3, 4, 5, 6. All right, and now I draw the rectangles slightly different way here. So here this rectangle area is 1. Since they're width 1 and the height is the function value, so when I plug in 2 here, is 2 squared, so 1 over 2 squared, right? 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, 1 over 6 squared. Okay. All right. So now setting up my sum here, right? So I want to set up an inequality again, right? So here to compare it, k, we get 1 plus 1 over 2 squared plus 1 over 3 squared, right? And notice the difference here is that at each step of the way here, the rectangles are below the curve, right? So that means that when I do this, right, my inequality is going to be less than. I do also have to be careful here. My integral is not going to go to 0 since it's undefined at 0, so I'm actually going to start my integral at 1, right? But I have to make sure that in order for this to be done appropriately, right, I have to remember that the area calculator will be from 1 to k. Make sure to add that 1, right? So 1 plus the integral from 1 to k in this case, right? Notice here, before it was k plus 1 because we went 1 a little, the other one ended at 1/5. This one does end at 1 over 6 squared. So we get 1 over x squared dx. Okay. All right, and again, the reason for this being different than before, right, I can't start my interval at 0 since it is unbounded at 0. Okay. All right. And now here, what we've done here, evaluating this integral, now here, this is just using the power, right, x to the negative 2, right? So the integral that we get here is 1 minus 1 over x, evaluated at k and 1. And then this becomes evaluated at k, and then at minus 1. So all in all, we get 2 over 1 minus k. All right, so what we have here, let me rewrite this here. So we have that the kth partial sum, which is again the sum from n is equal to 1 of k of of 1 over n squared. Okay. Is less than 2 minus 1 over k. Okay, and now if I let k go to infinity, two minus 1 over k, that 1 over k is going to 0, so this goes to 2. So now what I've established is that s sub k is less than 2. All right, now notice different than before, right? Here, I have bounded my sequence from above. Okay, so I bounded my sequence from above. Now that's not enough to tell me convergence, right? Because it could be oscillating between values, right? So what I'm doing here is the kth partial sum, right? If I plot all the partial sums here, what we're doing here is if that's 1, 2, I've created a bound for it. Right, so 1 and then 1 and 1/4, right? So I created a bound of this, but now the next thing I want to show is that's not enough, right? I need to show from when we started talking about series and sequences, right? I need to show that it is bounded and increasing, bounded from above and increasing, then I will show convergence, right? Well, if I take a look at the k sum, well, the k sum is nothing but s sub k minus 1 plus 1 over k squared, right? And if we just look at values for k greater than or equal to 2, right, starting here, we could see, well, this value here is always positive, right? So it's always increasing by some amount, right? So that means that here, the s sub k is increasing as well. So it's increasing and bounded, so that means that here what's happening is that at each step of the way, the kth partial sums are increasing, but they're always less than 2. Okay? So what that means is that it is converging to a finite value, right? The partial sums, right? As k goes to infinity. So that together, bounded plus increasing, right, tells me that, therefore, the sum n goes to 1 to infinity of 1 over n squared converges. Okay. All right. And that is how we apply the, so this is kind of examples going through kind of how the integral tests work. Right now in applications here, the theorem states this. Right? Suppose that a sub n is a series with positive terms, right? And the two sequences that the two series the two series that I was looking at, they both have positive terms, right? 1 over n or 1 over n squared, where n is bigger than or equal to 1. They were all positive terms. Okay, so that held. Right? And if that's the case, and it follows the 3 following conditions, it's continuous, right? F is continuous, right? The corresponding function, which for our interval was, right? F of x over 1 over x and f of x over 1 over x squared, looking at the domain being 1 to infinity, continuous, and also decreasing, right? If you take the derivative of both of those functions, you'll see that on the domain, always negative, so always decreasing. And then f of n is equal to a sub n for all integers, which we did, right? The way we set it up, those rectangles, right, were on the function values based off the function values. So all 3 of those conditions were held. So in application, this is how we're going to apply the integral test, right? We'll set up an improper integral, going from n to infinity. Right? And then from there, we'll evaluate. Now, if the improper integral converges, so does the infinite series. If the improper integral diverges, so does the infinite series. Okay, so straightforward, right? It all comes down to making sure those three conditions hold and evaluating an improper integral. And the convergence divergence of the improper integral is also the convergence divergence of the infinite series.